Hello viewers, welcome to CEC lecture. I am Dr. Preeti Jagwani from Aryapat College, University of Delhi. So today's topic is one of the very powerful string matching algorithm, that is Knuth Morris Pratt algorithm, which is commonly known by its short form, which is KMP algorithm. So in our previous lectures we have seen what actually the problem of string matching is, and then we have seen how this naive string matching algorithm works. So it is just shifting the pattern by one place in one iteration, and then it is comparing all the we can say matching characters, and wherever this matching is being broken, that shift is occurring again. So what actually the problem, or what actually the pros and cons of this naive string matching algorithm? So looking at this naive string matching algorithm and looking at kind of we can say other algorithms, we can say no pre-processing of pattern is required. There is no pre-processing phase, and because of that the running time of naive string matcher is equals to its matching time only. So no extra pre-processing time is added, because there is no provision of pre-processing, although that pre-processing is going to help us in future, but unfortunately or fortunately we can say both the sides of the coin are there. There is no pre-processing phase, and if there is no pre-processing, that means we are not encountering anything special which is to be stored or which is to be kept a track of. So no extra space obviously is needed, and we can say but on the other hand, the disadvantage is the naive method, I can say, is very inefficient because the information from a shift is not used again. So when I can say there is information from a shift is not used again, what does this mean? Let us consider this. So whenever a character mismatch is occurring, and let us assume that character mismatch is occurring after matching of several characters. For example, we have seen in our previous lectures, we have seen so many examples of such type, but even after matching several characters, let us say one character mismatch. So what my naive algorithm is doing? My naive algorithm is starting the comparison by going back in the form of character which follows the last beginning character. For example, I have got a match of A, but I am not going to get a match of B. So what is happening? When the next shift is occurring, my algorithm is again matching that A, but that A has been already matched. So whenever there is a character mismatch after several matches, the comparison begins by going back in from the character which follows the last beginning character, and here is, I can say, the bottleneck or the problem with naive matching algorithm. So here we have one savior for us, which is the agenda for today, or which is the topic for today, that is Knuth Morris Pratt algorithm, KMP algorithm. So KMP algorithm is going to give us the linear time for exact matching, and it compares from left to right, while my naive algorithm can compare from right to left also. That is one kind of flexibility we have got in naive string algorithm, but that flexibility is going to be very, very costly, because I can say this the worst case time is going to be order of n multiplied by m, where n is the size of the text and m is the size of the pattern. So here my Knuth Morris Pratt algorithm, what it is going to do, it is going to shift more than one position in one iteration, and this more than one shift is we can say is achieved by a pre-processing approach of pattern. So, that means the pattern which is to be looked for into the text, that has to be pre-processed first in order to avoid trivial comparison. So, what kind of trivial comparison I am talking about here is I will be explaining in a moment. So, the basic idea, if we can say, of Knuth Morris Pratt algorithm says that whenever we are detecting a mismatch, and that mismatch is particularly after some matches, we are aware of some of the characters in the next window. Obviously, for let us say, for example, we have compared the character number 1, 2, 3 and they all are matched, while 4 is not mismatching, and now I am shifting my pattern by 1. So, now the comparison is starting from 2. So, the comparison is working with the character number 2, 3, 4 and 5, but till 2, 3 and 4, that's the mismatch of 4 and the match of 2 and 3 are already known. So, we are aware of some of the characters in the next window of the text, and we must take the advantage of this information in order to avoid the matching of characters which we are aware that they are going to match anyways. So, let us try to understand this whole concept with the help of some examples in a moment. So, here we can say this KMP algorithm is what actually it is doing. So, in technical language I can say this KMP algorithm is using the degenerating property. Degenerating property of the pattern. Degenerating property says that pattern is having same sub patterns appearing more than once in the pattern. There are some sub patterns which are appearing more than once in the pattern, and this property is known as degenerating property. So, of this degenerating property, my naive string matching algorithm was not using it at all, but KMP is using this for pre-processing of the pattern, and by this pre-processing of the pattern, by using this degenerating property, it is going to improve the worst case complexity to order n, while the worst case complexity in case of naive string matching algorithm was order mn. So, obviously, it is a kind of, we can say, a considerable improvement. So, what KMP is doing extra? So, KMP says I am keeping the information that naive algorithm wasted, and that information was gathered during the scanning of the text. So, that there is no record of the previous scan of the text or any pre-processing kind of any pre-processing task of the pattern in naive matching algorithm, while Knuth Morris Pratt algorithm, KMP algorithm, is going to take care of this, and by this it is going to minimize the total number of comparisons of the pattern against the input string. So, basically it is avoiding the waste of information, and by avoiding this waste of information, a running time of order m plus n as compared to order m into n of naive string matching algorithm, and running time of order m plus n has been achieved. So, now I was telling you what extra work, or what kind of, we can say, what processing this KMP algorithm is doing extra. So, KMP algorithm is doing the study of pattern, and how it is doing the study of pattern. Now, let us say we have a text which is of AA, AA, AA and AB, and the pattern is triple AB, which is AA, AB. And now what it is doing? So, let us say j is the counter variable for pattern and I is the counter variable for text. So, for j and I equals to 0, 1, 2, it is matching. For 3 it is not matching. So, when it is not matching, first of all my KMP algorithm says I need not to backtrack I, only just j will be moved in the pattern, and that too not at the starting, but just onto the A just before the B. So, that means we have 3 A's in this pattern. So, in case of failure at the 4th position, where my A is not matching with the text of A in the text is not matching with the B in the pattern. So, now J will be moved back to the A which is existing just before the B. It will not move to A in the starting. So, this is what it is going to do. So, how? Let us try to understand this with the help of some examples, or we will be adopting some kind of specific terminologies which are there for KMP algorithm. So, KMP algorithm uses some terminologies related to prefix and suffixes. So, let us say we have a pattern which is ABC, D, ABC, and if we look for what are the available prefixes, you can go for as many as prefixes you need. So, let us say we have A is the prefix, valid, then AB is the prefix, very valid, then ABC, and then ABCD. Let us say we are stopping at 4. So, these are the prefix. For suffix, I am going to start from the back direction. I am having C, then I am having BC, then I am having ABC, and then I am having DABC, and now again I am here stopping at 4. So, what I did for the pattern, it is not for the text, we need to be very careful with this. So, for the pattern we have looked for the available prefix and suffix, and now we need to look whether there is any prefix which is equals to suffix. So, A, let us say let us start exploring the prefix list. So, prefix list is having A. So, we do not have A in the suffix which we have kind of written here. Then AB, no, AB is also not matching. Then we have ABC, yes, ABC is matching. So, ABC is one sub pattern here or one term here which is available as prefix and which is available at suffix also. So, here you can see ABC at the starting and ABC at the ending. So, as prefix as well as suffix also. So, basically what are we looking for? We are looking for the sub patterns where my prefix is equals to suffix. So, KMP is going to check whether there is some beginning part of the pattern which is appearing again in the pattern. That is what the I can say key work which is KMP is doing. And in order to we can say do this, what my KMP what the KMP algorithm is doing, it is generating an LPS table, or this is also known as pi table. LPS is longest prefix which is a suffix. So, obviously we are looking for the longest one. So, longest prefix which is also the suffix, LPS table for the pattern, and this table is going to recognize the longest prefix which is also a suffix. Now, let us take the examples of LPS. Let us consider a pattern which is given on the screen. So, we have AB, then CD, AB, E, AB, F. So, starting from AB, A is not common, B is not common, C and D is not common, but A and B are occurring again in the given pattern as it is given on the screen. Then E we do not have, then again A and B we have. So, AB here is such a sub pattern in this given example which is occurring again in the pattern. So, AB is at position 0 1, then AB at position 4 5, and AB at the second last and last third position we have. So, how this LPS table will be formed. So, in order to form this LPS table, the first thing which we will be taking care of is that we will start the indices from 0, and that I will tell you how. So, here A no match as of now, B no match as of now, C no match as of now, and D also no match as of now. So, we have written 0 0 0 0 here, but the next A which is after D is matching with the A which is at index number 1. So, that is what I was saying, we need to start indices from 1. So, A at 1, B at 2. So, what this information is saying? This information is saying the occurrence of AB after D is matching with the occurrence of AB which is at index number 1 and 2. Then E we do not have, so 0, again A and B, and this A and B is again matching with 1 and 2, and rest of them are 0. So, this is what we can say, this pre-processing of pattern is required, and when we will encounter these indices or these matching indices into the table, that is going to form an LPS table. I will show you in a moment. So, coming to the next example which says A B C D E, then A B F A B C. So, A B C D are not here, neither E, then A and B again at position number 1 and 2 are there, and then again A and B at the position number 1, 2, and yes, C is also at 3. So, A, B, C of the initial indices is occurring as a pattern A, B after E and A, B, C at the last. So, we are just writing the indices with which the character is matching at the end. And whenever I am going to kind of we can say enclose this in a table, so I will be having my LPS table. Looking at this example which is given on the screen, I am having A. So, A at the second position is matching with the first A, then A at the third position is matching with the A of the second position as well as of the A of the first position also, and similarly we are just going to write the indices with which it is matching. So, here is a table which is known as LPS table, or it is known as prefix function pi table, which is doing what? It is pre-processing the pattern to find matches of prefix of the pattern with the pattern itself. So, we are looking, we are in search of sub patterns within the pattern. So, this pre-processing step of KMP algorithm has nothing to do with text as of now, and then we can say the prefix function pi or LPS table, it is defined as a size of the largest prefix that is also a suffix. So, that what we are looking for, and this is what we have established in the starting of the lecture too. So, by this I mean how this KMP algorithm is going to use this pre-processed information. So, this pre-processed information, or I can say my this prefix table pi, or the LPS table, longest prefix, which is a suffix table, is indicating how much of the last comparison can be reused if the comparison is failing at a later stage, and also it is going to enable the avoidance of backtracking on the string x. So, let us say we are maintaining a counter in the name of the variable I on the text. So, this I will never backtrack. If j is a counter variable which is being maintained on the pattern, j can backtrack, but I cannot be backtrack, and as I is not backtracking, the number of we can say complexity of the algorithm will be, I can say, in terms of linear of order of n. So now let us take the let us take one example of Knuth Morris Pratt algorithm with a set string and a pattern. So here one thing which we need to be very careful is there is no backtracking in text, and the string is, I can say, A B A B C A B C A B, and that is the string, and please consider the first character of the string as a smaller a, and I am sorry here for the typo. Then AB ABD is the pattern. So what I need to do in case of this KMP algorithm? First of all, irrespective of the text or irrespective of string, I need to look for, or I need to make one table which is LPS table. So in LPS table, I will be looking for sub patterns within the pattern. So pattern I am having as A B A B D. So what it is happening? So A, first A has never occurred, Z, B never occurred, 0. Then I am having A. Yes, A is there, which is available. So A is the character which is matching with the character A available at index 1, and I have already told you that we are beginning with the index as 1. We can also begin with 0, but that's this index 1 will solve some purposes later in the comparisons. Then B is also present at number 2. So we have written 2 beneath B, and then D is not present here. So now my LPS for this pattern AB ABD is actually 0 0 1 2 0, having these pattern indices. And you can see here you can see this on the screen that AB ABD and the indices with which these characters are matching are written beneath these characters, under these characters, A0 B0, A with 1, B with 2, and D is not matching. So D is 0. Now on the top row, what I did is I have actually given the numbering, that is indices 1 2 3 4 5, and I have also reserved one index 0, which we will be seeing that how this reserving this index 0 is solving some purpose later in the comparison. Now coming to this text thing. So now we have a set pattern LPS table for this pattern, and for the text which is AB ABC, the whole text is there, and we have written indices. So 1 2 3 4 till 9, then 10 11 12 13 14 and 15. And now we are taking two counter variables. One variable is for I and another variable is for j. Now we have to be very careful that see what is happening here. Here I will be is comparing I with j plus 1, and if there is a match, I will increment both of the variables. For example, I, which is at the position number 1, A is available, j plus 1, j is at 0 initially, and at j plus 1 is A, that is available. I will be shifting I as well as I will be shifting j. So I has been shifted to B and j has been shifted to 1, which is A, and then I will be comparing I with j plus 1. Again they are matching, right? Then in the next iteration, I has been put up on A, which is at the position number 3, j is at the position number 2. There is again a match, again shift I and j both. Now I is at B and j is at the position number 3, which is at A. So j plus 1 is B, which is matching with the I. Till this point we are set. AB has been meshed, and the moment we are incrementing it, so the moment we are incrementing, I has acquired the position 5th position, while my j is at the position number 4 after incrementing. Now I am trying to compare j plus 1 with I. So that means this D is being compared with C. Now here is a mismatch. Here is a mismatch. So in case of mismatch, I will look at J. I will not shift I to back. I is not going to backtrack. I will be at that position wherever this C or this position number 5 is available. Now J is at the position number 4 in the pattern, which is representing B, and before B we have written 2 in the prefix table. So that means now J will be backtracked to the index number 2, which is B again, and it is having 0 beneath it. So now my J is at B, which is at 2, and then my I is at position number 5, which is C. So now again the comparison of I with j plus 1. So j plus 1 is A, and comparison of I, which is C, obviously not matching. So in case of not matching, again I will not backtrack instead I will backtrack J. Now where to backtrack J? I will be backtracking J to 0, because 0 is the number which is written beneath B in the pattern LPS table. So my J is at the position number 2, and please see that column, and in the last row of that column the number is 0. So now my J is at 0. Now I am again comparing with j plus 1 and I. So j plus 1 is A, and I is still at position number 5, which is C. So no match. So now I need to backtrack J again, but now my J is already at 0. It cannot be backtracked more. So what is happening? So here it will stay at 0, and then I will be incrementing I. So the moment I increment I, my I is going to be at position number 6, which is A, and then comparing it with j plus 1, it will be getting a match. So again we will get a match, we will get a match for B also, and so on and so forth. So the idea here behind this KMP table is we need not to backtrack I completely, only we will be backtracking J, and that too not to the first position always, but to the position which is given in the prefix table or the LPS table. So in this way we will be able to handle the movement of I and J. So I it is not backtracking even once. So when it is not backtracking even once, just the pre-processing step is extra here, but if you can see the complexity of the algorithm, it is going to give you the complexity of order m plus n, where m is for pre-processing of text, and while n is for this whole exploration of I is equals to 1 to n plus 1 in the sense we can say. So this is what the complexity of Knuth Morris Pratt algorithm is, and here in this given example it is going to have a valid shift, or it is going to have a valid matching for the last 5 characters, which are AB and ABD. So here in this lecture we have explored what are the problems with naive string matching algorithm and how those problems can be tackled in Knuth Morris Pratt KMP algorithm, and that KMP algorithm is shown in detail with the help of examples. So thank you for a patient hearing. Hope you have enjoyed the lecture.